Hello, hello, hello. In this episode of What's the Big Idea, we're going to continue to explore the connection between Newtonian mechanics and calculus. Isaac Newton, in fact, invented the mathematics of calculus for the purpose of solving some problems in classical mechanics. We've previously talked about the ideas related to differential calculus. So, for example, we in a previous episode of What's the Big Idea, we talked about the way we could define the instantaneous velocity of an object as just the derivative of how the position of the object is changing with respect to time. So, for example, if you have a situation where you know how the position of the object is changing as a function of time, say given by this red curve, and you wanted to know the velocity of the object at any point t, you just have to differentiate this curve. So if we want to know the instantaneous velocity of the object at time t equals 1 second, we just need to know the slope of the tangent line. So that is a way that we can go from an x of t graph, x versus t graph, to velocity just by taking the derivative. In this episode, we're going to work backwards. We're going to talk about the idea from calculus of integration, which is in many ways a kind of inverse process to taking derivatives. So let's dig in. So the problem I'd like us to consider is, given some knowledge of how the velocity of an object is changing as a function of time, can we find how the position of the object is changing in time? And that's a general sort of problem we want to consider. And again, to keep things simple, we'll continue to think about a one-dimensional world in which the object's position is just the object is moving back and forth along a straight line. So its position along that line can just be given by a simple variable x. And similarly about the velocity is either pointing to the right for positive values of the velocity or pointing to the left for negative values of the velocity. So let's start with sort of the simplest case imaginable. Let's imagine that the velocity of the object as a function of time is just a constant. The object continues at all times to move with a velocity v naught. And we'd like to know what the change in position is during some time interval between an initial time t sub initial and some final time t sub final. Well, that's easy. The change in position during this time interval, delta x, is clearly going to be just equal to v naught times delta t, where delta t is the difference in time between the initial time and the final time. And notice that this quantity, v naught times delta t, just corresponds to the area of this rectangle that I'm shading in. It's just the so-called area under the curve, the area between the curve and the horizontal axis. That shaded yellow area is just equal to v naught times delta t. And if we wanted to make a graph of how the position changes as a function of time, that's pretty easy. Also, if the time t equals 0, the object is at position x naught, then clearly as time progresses, the position will change its position linearly, and x of t is just equal to x naught plus v naught times t. So a graph of x versus time in this case would just be a simple straight line with a slope of v naught. Okay, what about more generally? Let's consider a more general case illustrated here where v of t has some arbitrary shape, and we'd like to calculate the change in position, calculate the change in position during the time interval delta t, where delta t is the time between some initial time and some final time. So that's the problem we'd like to solve. Okay, so here's the big idea. I am going to imagine dividing up this time interval between Ti and Tf into little tiny time intervals, and we'll call the duration of each one of these tiny time intervals delta t sub n. And we'll make each one of the time intervals the same value, the same width. Um, Well, since this time interval is relatively short, the velocity of the object doesn't change very much during that time interval. And so we can treat the velocity during this short time interval as essentially constant. And then we can just make use of the result that we had from the previous case. We know what to do during an interval in which the velocity is constant. So the change in the object's position during this one particular time interval, we'll call that delta x sub n, that's just equal to v sub n times delta t sub n. And that you'll recognize is just the area, this purple shaded area here. So we could also call this quantity a sub n. And if our goal is to calculate the total change in positions from this initial time t sub I to some final time t sub f, then really all we have to do is add up all the individual changes that occur during each of these very short time intervals. So we can write that delta x is equal to the sum of all the different delta x sub n's. And that's equal to the sum of v sub n times delta t sub n. Now, really should be a little bit more careful here. I've been a little bit sloppy by writing an equal sign here. The total change in position, I really should be putting wavy lines here because, after all, we did make a little bit of an approximation. It's really the velocity, of course, is not exactly constant during each of these um, time intervals. So it's not exactly correct to calculate delta x sub n just by multiplying v sub n times delta t sub n because the velocity is in fact changing. So this should be a squiggly sign here. But, and here's the key observation, this approximation becomes better and better if we're willing to make the time intervals delta t sub n smaller and smaller, because the smaller and smaller that these time intervals become, the less time there is for the velocity to vary, and therefore it becomes a better and better approximation to treat the velocity as being constant during those very short time intervals. So then what we can say is that the equality becomes exact. Delta x is exactly equal to this sum in the limit that delta t goes to 0. So in the limit that delta t sub n goes to 0, in the limit that delta t sub n goes to 0, delta x, is equal to the sum over n v sub n times delta t sub n. And hopefully you can recall, this should look familiar to you from your introductory calculus class, that another name really for this summation in the limit that delta t sub n goes to 0 is what we call a definite integral. So we can abbreviate this sum as the integral from the initial time t sub I to some final time t sub f of v of t dt. And notice that in the limit that delta t sub n gets smaller and smaller, the sort of gaps in here become smaller and smaller. And in this limiting case of delta t sub n going to 0, the situation of the thing that we're calculating really corresponds to what we call the area under the curve, the area of this gray shaded region. So this we can write is equal to the area under the curve. Now, one point that needs some clarification here. In this particular example, I showed an example in which v of t was always a positive number. So that meant that positive velocity means the particle is always moving to the right in this example. So as time progresses, delta x is going to continue to increase the longer the time is, the greater delta x is, because you're always moving to the right. But you can imagine a situation in which, say at some later times, the curve, the velocity versus time curve, eventually becomes negative. And so in this region here, now the velocity is negative, which means you're moving to the left. And the consequence of that is that in that case, this area here, which I'll shade in gray here, this now needs to be treated as a negative number, a negative area, because at this point, your delta x is decreasing because the object is moving to the left. So we can still say that delta x can be calculated from the graph of v versus t by looking at the area under the curve, but just be forewarned that when the v of t graph goes negative, the area that we're including has to be treated as a negative number. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.